What if I told you that Earth is constantly under threat from something far beyond our control? Picture this: a massive asteroid, hundreds of meters wide, hurtling toward us at unimaginable speeds. No, this isn't the plot of a new disaster movie. This is the reality we could face. While it might seem like something out of a science fiction thriller, it's closer to the truth than you think. Every day, Earth is bombarded with thousands of asteroids and space debris, some as small as a grain of sand, others as big as skyscrapers. And while most of them burn up in the atmosphere or harmlessly miss our planet, there's always the possibility, however small, that one could make impact. Now, let's get real. Just how dangerous are these cosmic threats? Well, NASA estimates that there are more than 25,000 near-Earth objects, NEOs, that could pose a risk, and they're actively tracking and monitoring more than 90% of these objects. Still, that's just the ones we've spotted. The universe is vast, and there are countless other asteroids out there that remain untracked, potentially on a collision course with our planet. In fact, we could be mere months or even weeks away from an asteroid strike that would change everything. Something like the asteroid that wiped out the dinosaurs 66 million years ago. Yep, it's real and it could happen again. But here's where things get interesting. In 2022, humanity took its first significant step toward planetary defense. Enter NASA's DART mission. For the first time, we launched a spacecraft with the specific purpose of testing a method to stop an asteroid from hitting Earth. It was a bold experiment, a statement to the universe that we're not powerless against these space threats. This wasn't just a test of technology. It was a test of humanity's ingenuity, determination, and will to survive. So what exactly is DART, and how did it manage to succeed where so many theories before it had only speculated? DART stands for the Double Asteroid Redirection Test, and its goal was deceptively simple: smash a spacecraft into an asteroid at high speed to see if we could alter its orbit. Sounds like something out of a James Bond movie, right? But there was a method to this madness. NASA selected the perfect target for the mission, a binary asteroid system made up of two rocks orbiting each other in space. The primary target was Didymos, a large asteroid about 780 meters across. Its moonlet, Didymoon, or as it's more formally known, Didymos B, was the real target, much smaller at around 160 meters in diameter. The key here was that Didymoon was close enough to Earth that it was within reach of a spacecraft, yet far enough that a collision wouldn't be catastrophic for us. It was the ideal testing ground, a controlled environment where failure wouldn't lead to disaster. Now imagine a spacecraft the size of a refrigerator, traveling at speeds of 15,000 miles per hour, faster than a bullet from a rifle. The DART spacecraft had just one mission: to collide with Didymoon at precisely the right angle and speed. In essence, NASA was attempting to hit a moving target in deep space, a feat that had never been attempted before. The moment of impact was a tense one. As DART closed in on Didymoon, the mission team watched nervously from Earth, knowing that a successful test would prove humanity's ability to alter the path of an asteroid if ever a real threat emerged. And then it happened. On September 26, 2022, DART slammed into Didymoon. The results were immediate and extraordinary. By changing Didymoon's orbit, DART demonstrated that it's possible to deflect an asteroid's path, and that, in theory, could save Earth from certain destruction. But here's where things get complicated. While the success of DART was groundbreaking, it was also a reminder of just how much we don't know. Let's talk about the science of planetary defense for a second. The fundamental idea behind DART is that if we can alter the velocity of an asteroid even by a small amount, over time, that slight change will compound and significantly alter the asteroid's trajectory. This is known as the kinetic impact technique, where the kinetic energy of a fast-moving spacecraft is transferred to the asteroid on impact, nudging it off course. Simple in theory, but as you can imagine, putting that into practice is a whole different ballgame. What makes DART so impressive is that it worked with a small target, Didymoon. But what if the asteroid we're dealing with is much larger, or faster, or even harder to track? Think about it. Didymoon was only one of many billions of asteroids in our solar system, and it wasn't even on a direct collision course with Earth. What happens when we face a true doomsday scenario, one that involves an asteroid much bigger than Didymoon, or one that's traveling at a speed that no spacecraft could match? While DART's success proves that planetary defense is possible, it also raises some uncomfortable questions. For instance, how many of these objects are out there, lurking in the vastness of space, waiting for the right moment to strike? Despite our best efforts, we can only track a fraction of the asteroids that might pose a real risk. While NASA's Near-Earth Object Program has made tremendous strides, we still have a long way to go before we can confidently say that we've spotted every asteroid that could potentially wipe out a city, a country, or even civilization itself. Let's also consider the timeline. As of now, we don't have a full-fledged planetary defense system. Sure, DART was a major step forward, but we need more than just one spacecraft. We need multiple strategies, backup plans, and collaboration between nations. An asteroid strike is not something that will give us years of warning. In fact, some of the most dangerous asteroids are the ones we don't even see coming until it's almost too late. And here's the real kicker. There are debates among scientists about whether deflecting an asteroid is the best solution at all. What if nudging an asteroid in one direction just sends it toward another population center, or triggers a series of unforeseen consequences? What if the energy released by a kinetic impact is enough to break apart the asteroid into smaller, yet still dangerous fragments? Some experts argue that we should focus on developing a variety of approaches, like gravity tractors, nuclear deflection, or even capturing the asteroid and moving it with rockets, to make sure that we have the flexibility to handle different scenarios. As we look to the future, the DART mission serves as both a victory and a warning. Yes, we can redirect an asteroid, but can we do it in time? Will we be ready if a truly catastrophic object is discovered on a collision course with Earth? The stakes are high and the clock is ticking. Take a moment to think about that. What if the next asteroid isn't one we can handle with a single test mission? What if, instead of the DART spacecraft, humanity's only hope lies in a much more complex, far-reaching effort to save Earth from certain destruction? Now that we've established the sheer magnitude of what the DART mission accomplished, let's step into the heart of the mission, the science and technology that made it all possible. How did NASA pull off this monumental feat of sending a spacecraft millions of miles away and striking an asteroid dead-on at such an incredibly fast speed? And what makes this method of planetary defense so critical to our future survival? To truly understand the brilliance of the DART mission, we need to look at a combination of physics, engineering, and sheer ingenuity that made it all happen. So buckle up. This is where things get really interesting. First, let's break down the problem. We've got an asteroid and we need to redirect it. That seems simple enough. After all, we've been launching rockets and spacecraft into space for decades, right? But here's where it gets tricky. In space, there's no easy way to slow down or speed up objects once they're in motion. In fact, it's incredibly difficult to change the trajectory of something traveling at such high velocities. DART's mission was to test what's called the kinetic impact technique. In its simplest form, this concept is based on the idea of a moving object transferring its momentum to another. Think about a bullet hitting a target. The bullet transfers its energy into the target, which can push it out of the way. The same principle applies here, but at a much grander scale. To visualize it, imagine this. DART's spacecraft was about the size of a refrigerator and weighed about 550 kilograms. It was headed toward Didymoon, a small moonlet of the much larger Didymos asteroid. The mission's goal was to hit Didymoon with such precision and speed that it would slightly alter its orbit around Didymos. The hope was that even a tiny nudge would be enough to change its path, just by a fraction of a degree. But that tiny change could make all the difference. Over time, this would accumulate, potentially altering the moonlet's trajectory enough to prevent a collision with Earth in the future. Now here's the cool part. Speed. DART wasn't just casually flying into space. The spacecraft was traveling at 15,000 miles per hour. That's 24,000 kilometers per hour, faster than a bullet shot from a rifle. To put that into perspective, DART was moving so fast that if it hit anything even slightly off target, it would completely miss. Imagine aiming a dart at a bullseye from the other side of the room and having to hit it while standing on a moving train. That's the level of precision we're talking about, and it didn't stop there. The mission had to account for the fact that Didymos was not only moving through space, but also rotating as it orbited Didymos. DART had to not only hit a moving target, but also predict the exact moment it would collide with Didymos. Despite all the forces at play, it's like trying to hit a moving car with a dart while the car is constantly changing speed and direction, and you're in a spacecraft that's accelerating faster than a Formula One car. To accomplish this, NASA didn't rely on human intervention. Instead, DART was fully autonomous, guided by onboard cameras and navigation systems. The spacecraft's most crucial tool was its Draco camera system, which was designed to capture high-resolution images of Didymos in real time. As DART approached its target, the camera was able to lock onto the asteroid and make real-time adjustments to the spacecraft's trajectory. This system was so advanced that it could make decisions in milliseconds, ensuring that, despite the vast distances and complexities involved, DART would stay on track to hit the bullseye. The final moments of the mission were captured by DART's camera, showing the dramatic and breathtaking collision. As the spacecraft crashed into Didymos, a shock wave of energy was released, transferring kinetic energy to the asteroid. But the true test came in the aftermath. Did the asteroid's orbit change? NASA had prepared for this by measuring Didymos' orbit around Didymos before the impact, and then again after. The goal was to measure how much the orbit was altered, and to everyone's surprise, the results were phenomenal. DART had successfully changed Didymos' orbit by around 33 minutes, a significant shift for a body in space. This wasn't just a minor tweak. This was proof that humanity had the capability to redirect an asteroid if ever needed. Now let's talk about why this is such a monumental achievement. Up until this point, the idea of asteroid deflection was mostly theoretical. Scientists and engineers had discussed various methods over the years, like nuclear explosions, gravitational tractors, or even sending a fleet of spacecraft to push an asteroid off course. But no one had ever tested these methods in real life. DART wasn't just a success. It was the first real-world demonstration that we could alter the trajectory of a space rock that could be a potential threat. But even with the success of DART, this was just the beginning. What NASA proved was that kinetic impact could work. However, it's not a one-size-fits-all solution. Not all asteroids are created equal, and some are much harder to deflect. The size, composition, and speed of an asteroid all play a significant role in how much force is needed to alter its path. The amount of energy required to deflect a massive asteroid that weighs millions of tons would be far greater than what was needed for Didymos. And what if the asteroid is spinning at an odd angle or has a complex structure? Let's consider another factor that could complicate things: the timing. The key to a successful deflection mission is having enough time to plan and execute. In the case of Didymos, NASA had years to study the asteroid and plan for the impact. But what if we don't see an asteroid coming until it's only a few months or even weeks away from Earth? Would a kinetic impact be effective with such little time to prepare? And what if an asteroid's trajectory is altered in a way that creates new risks, perhaps breaking it into smaller pieces that are just as deadly? These are the questions that NASA, along with other space agencies, is working to answer. While DART proved the concept, the next step is figuring out how to scale up and develop a full-fledged planetary defense system. This will require not just the technology, but also a global collaboration between nations, as asteroid impacts don't respect borders. And while DART was a huge leap forward, it's clear that planetary defense is a complex, multifaceted issue that requires many more tests, innovations, and approaches. Imagine for a moment that you're part of the team at NASA. You've just watched the DART spacecraft hit Didymos, and you've seen the success. You've proven the concept. Now you're thinking about the next big challenge. What happens when the next asteroid is bigger, faster, and farther away? Can we still pull off the same success, or will we need a new approach entirely? This question lingers in the minds of space scientists, engineers, and even governments around the world. The truth is, DART was just the first step in what will be an ongoing journey to protect Earth from the unseen dangers of space. But with each success, we get closer to developing the tools and knowledge needed to ensure that humanity won't just stand by if an asteroid ever threatens our planet again. The dust has barely settled from the DART mission, and already there's a question on everyone's mind: what happens next? Sure, DART proved that we can deflect an asteroid, at least in the case of Didymoon, but is this really enough to guarantee our survival? The fact is, planetary defense is a far more complex and uncertain challenge than it may seem. DART was a victory, yes, but it was also a wake-up call. As we look to the future, we must ask ourselves, can we truly protect Earth from the countless threats in space? And if so, how? The first major hurdle is the unpredictability of the objects we're dealing with. The universe is filled with asteroids and comets, some of which are too small to detect until it's too late, and others that are so far away we don't even know they exist. There's no easy way to track every potential threat, and many of these objects move so fast that there may not be enough time to react. What happens if we spot an asteroid just a few months before it's set to impact Earth? Can we launch a mission in such a short time frame? The problem isn't just about detecting asteroids, it's about the scale of the threat. Let's talk about size for a moment. DART's target, Didymoon, was a relatively small asteroid, but larger objects, like the one that caused the extinction of the dinosaurs, could be far more destructive. These space rocks can be hundreds of kilometers wide, and the force of their impact would be enough to cause catastrophic earthquakes, tsunamis, and an atmosphere full of debris, blocking sunlight and leading to a nuclear winter scenario. If an asteroid of that size were heading our way, deflecting it with a kinetic impact might not be enough. And that's where the true challenge lies. While kinetic impact is the most well-known method for asteroid deflection, it's not the only one. Scientists have been brainstorming various alternatives, each with its own strengths and limitations. Let's take a closer look at some of these ideas. Nuclear deflection, the Big Bang approach. One of the most controversial, but potentially effective methods is nuclear deflection. The idea is simple. Instead of gently nudging an asteroid, we could use the power of nuclear explosions to alter its trajectory. There are two ways this could work. One method involves detonating a nuclear bomb near the asteroid's surface, which would vaporize part of the rock and create a blast of energy strong enough to push the asteroid off course. The other approach would involve detonating the bomb directly on the asteroid's surface, using the explosion to send shockwaves through the asteroid and change its path. The upside to nuclear deflection is that it could be used on asteroids much larger than the one targeted by DART. In theory, this approach could work even if we only had a limited amount of time to prepare. But there are major risks involved. First, there's the possibility that the explosion could break the asteroid into multiple pieces, making things worse rather than better. Second, there's the issue of political and ethical concerns. Launching a nuclear bomb into space is no small matter, and it could invite global debate over the potential consequences of such an action. Gravitational tractor. The gentle push, another method being considered, is the gravitational tractor. This approach involves sending a spacecraft to orbit near the asteroid, using its gravitational pull to slowly and gently alter the asteroid's trajectory. The spacecraft would not collide with the asteroid, but instead it would use its own mass and gravity to tug on the asteroid, gradually changing its orbit over time. The advantage of this method is that it's less risky than a nuclear explosion and doesn't involve direct contact with the asteroid. However, it's also incredibly slow. The spacecraft would need to be in place for a long period of time, years, perhaps even decades, to make a noticeable difference. This makes the gravitational tractor better suited for asteroids that are detected far in advance, rather than those that are discovered just months before impact. The laser approach. Focused energy, another cutting-edge idea, is to use laser beams to vaporize part of the asteroid. This concept involves sending a spacecraft or satellite into orbit around the asteroid, where it would focus a high-powered laser on the surface. The laser would heat the asteroid's surface to the point where it starts to vaporize, creating a burst of gas that would push the asteroid in the opposite direction. While lasers could be highly effective for small to medium-sized asteroids, the problem is that they require a huge amount of energy and precision to work. Also, if the asteroid is rotating or has a complex surface, it may be difficult to focus the laser beam accurately enough to alter its trajectory. 4. The billiards method, asteroid capture. Now here's an idea that's almost like something straight out of science fiction, capturing the asteroid. The concept involves sending a spacecraft to either land on or capture an asteroid, then using it as a kind of cosmic pinball to deflect its course. This could be done by attaching a large tether to the asteroid or by creating an artificial gravity field to slowly pull it out of harm's way. This method could be incredibly effective for large, slow-moving asteroids, but the logistics of capturing and moving an asteroid are daunting. It would require immense energy and resources, and we still don't fully understand how to manage the mass of an asteroid once it's tethered to a spacecraft. Asteroid mining, a dual purpose. Approach, finally, there's an idea that could kill two birds with one stone, asteroid mining. Some scientists have proposed the idea of sending mining missions to asteroids not just to harvest valuable resources, but to test methods for asteroid deflection. By mining or breaking apart an asteroid, we could change its mass or structure, thus altering its orbit. This approach could provide useful data for planetary defense, as well as help alleviate Earth's resource scarcity. While asteroid mining holds promise, it's still in the early stages of development. The technology to mine asteroids and use them for planetary defense is years, if not decades, away. But it's an idea that could pave the way for a sustainable and proactive approach to deflecting space threats. So as you can see, there's no one-size-fits-all solution to the problem of planetary defense. Each method has its advantages, but also its limitations, and it's clear that we can't rely on just one strategy. A multi-pronged approach will likely be necessary to defend Earth from a wide range of potential threats. But there's a larger issue at play here as well: time. The clock is ticking. If we spot an asteroid just a few months away from hitting Earth, there may not be enough time to implement any of these methods. This is why it's critical that we continue developing our ability to detect asteroids earlier, refine our deflection technologies, and create global agreements on how to handle such a crisis. The world's space agencies, NASA, ESA, Roscosmos, CNSA, and others, must come together to create a cohesive, global planetary defense network. But here's the catch. What if we don't have the time to get it together? What if, like in the case of Didymoon, the asteroid is spotted just a little too late? Is there a point of no return? The reality is the next asteroid we face could be the real test of our ability to protect Earth. And as impressive as DART was, it was just the beginning. The future of planetary defense is still unfolding, and with it humanity's ability to survive the cosmic threats that loom above us. So, let me leave you with this. The next asteroid may not give us a warning. What do we do then? Are we truly prepared, or are we gambling with the future of civilization? As we approach the end of our journey, there's one critical question we need to ask. What does the DART mission and the larger concept of planetary defense really mean for humanity's future? What does it say about our place in the universe, our ability to protect ourselves from cosmic threats, and our ambitions to explore the stars? It's one thing to successfully deflect an asteroid, like Didymoon, but what happens when the stakes are higher? What if someday we're faced with a true end-of-days scenario, an asteroid much larger, faster, or closer than anything we've ever encountered? Let's take a step back and consider the bigger picture. The DART mission wasn't just a victory for NASA, it was a victory for humanity. For the first time in history, we proved that we can alter the course of an asteroid, and in doing so we confirmed that we're not completely powerless in the face of cosmic threats. But in some ways, this victory was just a first step. The fact that we can redirect an asteroid doesn't mean we've solved the problem. Far from it. The universe is vast and filled with risks we can barely comprehend. The DART mission proved our potential, but it also highlighted how little we truly know about the vast forces at work above us. It's important to understand that while we've made progress in tracking and identifying near-Earth objects, many asteroids remain out of sight. The space surveillance systems we currently have are impressive, but they're limited by both technology and time. As of now, we've only detected a fraction of the potential threats out there. There are still large asteroids hiding in the shadows of our solar system, objects that could potentially change the fate of humanity if they were to cross paths with Earth. But here's the hope. DART is part of a much larger global effort to protect Earth, and while that's reassuring, it doesn't negate the fact that we've only scratched the surface of what needs to be done. This mission showed us that planetary defense is possible, but it also revealed the fragility of our planet. One small asteroid could change the course of civilization. One miss, one failure, and humanity could be back to square one, facing extinction. So how do we mitigate that risk? The future of planetary defense is not just about technology, it's about global cooperation. In our interconnected world, where nations often struggle to align on even the most basic issues, space offers us a unique opportunity for collaboration. Asteroids don't care about borders. A threat to one country is a threat to all. The DART mission, though conducted by NASA, is part of an international effort to prepare for such eventualities. As the world moves toward a more collaborative approach to space exploration and defense, the need for a united response to potential asteroid impacts will become ever more pressing. But cooperation isn't the only challenge. There's a need for resources. Defending against asteroids is an expensive endeavor. Developing new spacecraft, technologies, and missions to detect and deflect asteroids requires not just scientific breakthroughs, but also vast investments from governments, private companies, and international bodies. As space exploration advances, we will need to ensure that funding is in place to support planetary defense initiatives, because, as the DART mission demonstrated, time is of the essence. Consider this. What if the asteroid we face isn't one that can be deflected by just one spacecraft or one method? What if it's larger than anything we've ever encountered, and all the deflection strategies we've explored fail? This is why backup plans are just as important as the main strategy. This is why we need a diversity of solutions at our disposal. The more approaches we have, the better our chances of survival. And this is where things get truly exciting. As humanity moves forward in its quest to explore the stars, the lessons we learn from planetary defense could play a pivotal role in how we prepare for deep space exploration. Asteroid mining and space colonization might seem like far-off dreams, but the reality is that as we explore space and look for new resources, we'll inevitably come face-to-face with asteroids on a regular basis. The technologies we develop to protect Earth from these threats could one day be used to fuel our ventures into the stars. Imagine being able to mine asteroids not only for valuable metals, but also to use them as stepping stones for further space exploration. What if we could build space stations around asteroids, or even set up colonies on them? The technological advances needed to protect Earth could be the very same ones that help us expand into the cosmos. The future of planetary defense isn't just about surviving. It's about thriving in a universe that's vast, unpredictable, and full of potential. But let's not forget the emotional and philosophical implications of it all. When we look up at the night sky, we see stars, planets, and the promise of infinite possibility. But we also see the terrifying truth that the cosmos is indifferent to our existence. Earth is just one small, fragile dot in the infinite expanse of space. The DART mission didn't just teach us about technology and physics, it reminded us of our vulnerability. And in acknowledging that vulnerability, we also embrace our capacity for innovation, collaboration, and survival. The DART mission is a reflection of the best of humanity, our desire to explore, to understand, and to protect. It's a beacon of hope in an unpredictable universe, a symbol that, when faced with seemingly insurmountable challenges, we can rise to the occasion. But as much as the mission was a triumph, it's also a call to action. We can't afford to wait until the next asteroid is just a few months away. The stakes are too high. So as we conclude this journey, ask yourself, are we truly prepared for what's next? What if the next asteroid is bigger, faster, and closer than we ever imagined. What if we don't have a DART spacecraft ready to save us? How do we ensure that we're ready to face these threats head-on, no matter what comes our way? I'll leave you with this thought. The universe is full of mysteries and dangers, but it's also full of possibilities. The DART mission didn't just save Earth, it gave us a glimpse into the future of space exploration and survival. And that future? It's ours to shape. What do you think? Is humanity ready for the challenges that lie ahead? Or are we still just beginning to understand the true scope of the threats we face? Drop your thoughts in the comments below. I'd love to hear what you think.